Training a machine learning model is, at its core, a massive spatial optimization problem. We drop an algorithm into a vast, multidimensional landscape of data and ask it to find the absolute lowest possible point of error. When this mathematical terrain is perfectly smooth, we rely on a foundational algorithm called gradient descent to navigate us downward. This chart shows how that engine runs. For any position on a smooth curve, the algorithm calculates the exact slope, the gradient. These downward arrows represent the steepest descent. By taking each step downward, it inevitably guides itself to the minimum error at the bottom. For perfectly smooth mathematical problems, this iterative process is intuitive, powerful, and flawless. But real-world machine learning architectures, like support vector machines, rely on loss functions that generate much harsher landscapes. This V-shaped graph illustrates the problem. Many effective models create sharp canyons in the data where a single clear slope doesn't exist. If you land at the exact bottom, traditional calculus breaks down. The function is non-differentiable. The gradient is completely undefined. This sharp edge stops the classic optimization engine dead in its tracks. To solve it, mathematicians had to invent a completely new directional tool. That elegant mathematical workaround is called the subgradient. This diagram shows how it works. Where a single gradient requires one perfect tangent line, the subgradient accepts any line, like these multiple tan lines, as long as it sits entirely below the convex function. Because there are many lines that can satisfy this rule at a sharp kink, it creates a whole collection of valid downhill directions, known mathematically as a differential set. When we upgrade to the subgradient method, this text block shows the critical change to the algorithm. Instead of freezing at an undefined point, it simply picks any valid vector from that differential set to keep moving. Comparing these two 3D graphs, you can see the difference in action. The smooth descent on the left is replaced by a jagged path on the right, as the algorithm bounces around the sharp canyon walls. The math is patched. Even on harsh, non-differentiable terrain, this method guarantees that we will eventually reach the minimum error. The math works perfectly on paper, but deploying it across modern AI datasets hits a massive physical limit. As this diagram illustrates, calculating a true subgradient requires the computer to map out this entire dense web of arrows. It has to process the loss for every single piece of training data you have. To take just one step downhill, the computer must run a summation across all examples. When a model trains on millions or billions of parameters, calculating that total for every single millimeter of movement becomes completely impossible. The subgradient method solves the geometry problem, but it fails against the hard engineering limits of computing power. To actually build large-scale models, engineers needed a workaround that bypassed this computational bottleneck. They found it in stochastic gradient descent. Instead of crunching the entire massive dataset, stochastic gradient descent uniformly samples just one single piece of random data. Looking at steps 1 and 2 of the algorithm, calculating the loss for one random point makes every update incredibly fast and cheap. By intentionally sacrificing the total precision of the full dataset, the algorithm gains a computation speed that scales endlessly. But throwing out billions of data points to rely on single, random samples sounds like a recipe for chaotic, terrible navigation. The reality of these random choices is a chaotic, erratic blue line zigzagging wildly through mathematical space. However, it works because of the unbiased estimator trick. The expected value of these random jumps averages out, creating a straight dashed line to the optimal solution. When dealing with massive datasets, embracing this random noise gets you to the target significantly faster than waiting for perfect calculations. We retain the theoretical guarantee that the model will learn and converge, but we finally have the speed required to execute it on physical hardware. This combination of generalized calculus and stochastic speed powers modern architecture. SGD serves as the central hub for today's computing-intensive fields. Massive neural networks for deep learning and immense natural language processing models only function by processing data one point at a time. Stochastic gradient descent solves both the mathematical kinks and the hardware limits. It provides the scalable mechanics that make the modern era of artificial intelligence physically possible.